Okay, we've learned about transition state theory from partition functions, usually molecular partition functions. This is usually implemented as the harmonic transition state theory, where we treat all of our vibrations as strictly harmonic. Whether we quantize those or treat them classically, there are a few variations within this category, but I'll just remind you that this was this so-called harmonic transition state theory, very widely used in practice in many different disciplines. We also learned about transition state theory from activation free energies, activation enthalpies, activation entropies. This is all coming from this thermodynamic formulation of transition state theory, and the main advantage of this one was that it allows you to interpret trends from experimental data. Okay, so very useful in the hands of an experimentalist, this particular variety. And we've learned about transition state theory from equilibrium average fluxes. All right, so the last bit that we want to cover before we move on to other things is to talk about variational transition state theory. And I want to begin by giving a qualitative motivation for where this idea comes from. It actually emerged very early in the days of transition state theory. Wigner said that you want to choose your dividing surface so that you minimize recrossing. Horiyuti said you want to choose your dividing surface so that you minimize the rate. Probably the latter is the more rigorous criteria in Q. And I have a region over here that is region of phase space that I'll designate to be my reactants. And then I have a region over here, and this is a region of phase space that I will designate as my products. And there's some region between that I can imagine might look something like a transition state in here. Okay? So now the question is, what is the ideal reaction coordinate and transition state surface to use? If I watch molecular dynamics trajectories on this surface, then I will typically see excursions from the reactant basin that will come out and they will do things like this. This one didn't quite make it over. This one is a transition path that's going to make it over to B. And then, of course, we also have excursions from B that don't quite make it to A. Maybe it's easy to come up here and do this. Let me keep that picture the way it is. And now what I want to do is to say, well, let's suppose that I used Q as my reaction coordinate, and then I compute the free energy surface just as a function of Q, ignoring this last variable Q prime. Now I'm going to draw another plot below this, sort of running out of space here. But my plot down below this will have a barrier, and this will be basin B over here and basin A over here. And if I look at where the maximum in free energy is along this barrier, this is a rather loose criteria. In practice, you'll see in the theory that we have to think about Jacobians and all kinds of things. But roughly speaking, we can say that the transition state location should approximately correspond with the location of the maximum in free energy along this coordinate Q. Okay, so that's this point right here. I'm going to lift that up. Okay, so here is my dividing surface that we got from this construction. All right, so now imagine what would happen. Hopefully you guys can see that. Let me just go ahead and draw that. I spent all that time making dotted lines. Just go ahead and draw that as a thick dividing surface. So this is my trial dividing surface. And this is the sense in which the transition state theory is variational. I could cut this space the way I drew it initially, or I could cut it the way I just did now. Transition state theory will give me two different rates. Because if I average all the trajectories that make little excursions from A, and remember in transition state theory we're only interested in the one directional escape rate. So what will happen? I crossed the surface once here, but it went back and it crossed here again. Transition state theory assumes that this trajectory crossing the surface will end up over here. This one came from that side and will end up over here. Transition state theory is going to count this one. That's okay. It should. This was an actual transition path. It carries flux from the reactants to the products. But transition state theory is also going to take this trajectory that came from B, crossed in the wrong direction, does not get counted by transition state theory, but then turns around and comes back and gets counted by transition state theory. So you can see that really this system we only had one transition path, but transition state theory counted three of them. It counted this crossing event, it counted this one, which it should have, and it counted this one, which it should. Okay? So the idea here is that when we have complex free energy landscapes, complex energy landscapes, where we have to guess with some uncertainty about which variables are the important ones, that's not always trivial to do, and there's a variational theory that tells us how to do it best. The idea is to choose the dividing surface so that we minimize the result of this transition state theory rate calculation. Okay, so in summary, I could end the lecture here if I wanted to. I want to minimize over all trial dividing surfaces the TST rate constant, which is really a functional of the constraints and functions that we use to parameterize that dividing surface. Okay, so that's the transition state theory rate. This thing is going to give us the VTST calculation. It's very easy to imagine saying, well, I want to use Q, but should I have put the dividing surface here? Should I have put it here? Here? Let's examine some of those. Okay, I just want to work in one little thing that I forgot to mention, and that's that really when we have a saddle point on a potential energy landscape that funnels all the flux through that one saddle region as part of the mechanism, then we don't really need variational transition state theory. The harmonic transition state theory construction in those special cases does an excellent job, and fortunately those special cases are quite common, right? So a lot of the machinery that you can download in software like Gaussian, like QChem, they have built-in algorithms for finding transition states that are identified with these saddles, and you can do the calculation. And the calculation that you're using, remember, is using that normal mode and the hyperplanar dividing surface, and that's really, within the harmonic approximation, as good as you can do. In fact, it's perfect if the harmonic approximation is correct. So I just wanted to mention that before we go on and talk about more complicated situations, that you always want to ask yourself, do you even need to worry about these issues? Okay, so recall that transition state theory counts every crossing of your dividing surface in the positive direction as a reaction. And some of these, though, are really just excursions, right? So sometimes that no recrossing assumption is going to be an approximation, and transition state theory is going to count those towards the rate. And that means that transition state theory is always going to give you a rate estimate that is larger than the real estimate, at least within the context of systems that have classical mechanics. And now, knowing that your transition state theory estimate is always bigger than the real answer, and that the way we do the transition state theory calculation is to choose a reaction coordinate and then place a dividing surface along that reaction coordinate, and these two choices both affect the number that comes out of our calculation, then to get as close as possible to the real answer, we should variationally minimize over choices of our reaction coordinate and where along that coordinate we place the dividing surface. If there's only one reaction coordinate to pick from, this becomes reaction coordinate Q, drawn here, and a free energy surface as a function of Q. And if I pick my transition state surface to coincide with the maximum in free energy, I can imagine that most of these trajectories that cross over the top of this barrier are going to keep on going. But if I instead placed it here, then I will get lots of these. This is an alternative choice for where I could position my dividing surface. And now what's going to happen is that I'm going to get a really lousy estimate of my rate of escape from A to B, because I'm going to get lots of these excursions from A that crossed. So this one crossed right here and then turned around and went back. So transition state theory is going to count that trajectory, and it should not have. Now you might think, well, then the obvious solution is to actually place your dividing surface way over here. I can, position my dividing surface way on the other side, and now I'm sure that everything that crossed over is going to ultimately make it onto B. Well, remember the way we do that calculation, though. It's the equilibrium probability to be at this point relative to the equilibrium probability to be at this point, multiplied by that velocity of crossing through this point. Okay, so now the problem is that at equilibrium, I don't know that there was a barrier between me here and here. I've had plenty of time to visit this point. And so what you'll now pick up are trajectories that are coming from the other side. And this one, came this way out of basin B, past my other trial dividing surface, and then went back through it. So transition state theory thinks that came from A, because it's going to assume that trajectory went to B on this side and came from A on the reverse. Okay, so these are the things that cause errors in transition state theory calculations. If you know which coordinate to pick, this is a rather simple one-dimensional line search to do a minimization, basically, and you just choose where along that coordinate you cut the space. And then your variational aspect of the calculation is done. Now, in reality, this reaction coordinate is one of 3n degrees of freedom, and just choosing that reaction coordinate itself can be a bit of a challenge. We're going to do a little example calculation here to illustrate variational transition state theory, and also to illustrate the calculation of transition state theory rate constants by this generalized transition state theory rate expression. This is I think, a really practical example. We've used this in the context of catalysis problems, and in this example, we're just going to think about two gas phase molecules A and B that are associated, and they're going to interact by this Morse potential. The Morse potential has three parameters. There's a well depth, E naught. There is a width of the well, which is controlled by this parameter A. When it gets big, the well depth gets narrow, and the bottom of the well is located at a position R naught. And so, all of this is done in terms of this dimensionless distance here. So what's going to happen is that these two things are going to sit here and rattle around, and maybe by a collision they will acquire enough activation energy to escape. And yet there's no saddle point on this landscape, right? And so that's going to create some problems for using the standard version of transition state theory with partition functions. Well, we can always go back and we can use this version of transition state theory, the generalized version. But then we have to choose, where do we place the dividing surface? Should I place it way out here when they're completely far apart? Well, the problem with that is that eventually I'll have molecules A and B that just come by each other and don't really collide, and yet transition state theory is going to count those as having crossed within that critical distance and then passed by each other. It will overestimate the rate because of that. On the flip side, if I place this dividing surface too close, then I will have little excursions from the reactant state that really didn't have enough energy to escape, and it will count those as reactions too. Okay, so somewhere in here we know that there's going to be an optimum place to position this dividing surface, and that's where we're going to use variational transition state theory. Our notes from a previous lecture, we know that we can calculate the rate as the absolute average velocity along my reaction coordinate at my trial dividing surface, which in this case is going to be a trial surface at RAB equals R star. And this will just be a variable in our theory. The rate is going to be a function of where we position this R star. Okay, and now the rest of this rate expression, we have the units of the rate constant. The units of my reaction coordinate, which is probably going to be in angstroms or something. And then we have a minus beta free energy of activation, and that free energy of activation is going to depend on where we put that dividing surface. Absolute velocity along a distance coordinate like this is going to be equal to, this requires some statistical mechanics to do these things. So we have 2 kBt, a factor of pi, and a reduced mass. All right, so this reduced mass could, in principle, depend on where we put that dividing surface. So I'll put a little star there just in case, so that we don't forget to think about that. And this reduced mass, in our case, is just 1 over the mass of A plus 1 over the mass of B. Okay, so we're really quite lucky here that this actually doesn't depend on where we position that dividing surface at all. So in this particular case, we don't have to think about that. But in general, you always want to be careful that you include the possibility that your reduced mass could be coordinate dependent. And the last bit, if we go through and we think about this Landau free energy, it's really a probability density when I put it in the exponential. So this e to the minus beta delta f evaluated at position R star, how do we calculate this in practice? Okay, so it's not going to be completely trivial to do this. Okay, so let's think about what this free energy is as a function of R star. So we're working with the exponential of the free energy, and we can construct that by remembering that what we're doing is taking an ensemble of reactants and transforming them into an ensemble of things that live at this dividing surface location R star. Okay, so the reactants will be in the basement, and the species on the dividing surface will be in the numerator. And so that kind of gives us a guide of how to construct this free energy expression. So we have dxa, dxb. These are the Cartesian coordinates of my molecules A and B. We have an indicator. Remember in our notes, you're going to have to go back and see the generalized transition state theory notes, but we did this with an indicator function that's going to tell us when we're in the reactant state. And when we're in the reactant state, we're looking for this AB merged distances. So we're going to have a distance threshold to say you're definitely in the reactants down here, e to the minus beta u of r. This is going to count, the partition function down here in the basement is going to be dominated by things that live down here in the bottom of this well. So we could even make a harmonic approximation, and we'll probably be okay with this. Okay, let's fill in the part of this calculation now for the transition states. Okay, so again, integrate over the positions of A and B, with vector signs over those to remember. And now, instead of having a whole region along the R coordinate that we're going to count as our reactants, we have a very specific place, R star, that we've chosen. And so because that's now a specific place, we're going to include it as a delta function here, R of x minus R star. And now we have our e to the minus beta u of r. Okay, so that's the numerator. If I go through and I think about, I have to remember back to equilibrium stat mech now. You're going to integrate over all the volume of your space. That's going to give you one factor of volume coming out of here, a change to spherical coordinates. Okay, now I cheated in going from here to here. I took a little time delay and wrote out the change of variables beforehand. Okay, so what we're doing is we're changing these six-dimensional integrals, 3 for the position of A, 3 for the position of B, and we're turning them into a spherical coordinate system where we just keep track of the distance between A and B, and that can be at any orientation, so we're going to have the usual polar angles. And we're also going to have the center of mass of A and B, and that's going to give us factors of the volume that we're integrating over. So the volume comes out, and it's in the denominator as well, and it's going to just cancel away. We don't really have to think about it. But when we do this calculation with the polar coordinates, we have to be pretty careful. Okay, so there are a number of things to think about that are going on in here in this calculation. Let me purposely cast a shadow over this so that you can not see the glare. All right, so downstairs we have 4 pi r squared from our conversion to polar coordinates. We have e to the minus beta u of r dr. All the angles have already been integrated. What's going on here in the limits is that we're counting everything from 0 up to r star, okay? And that this integral is going to be dominated by the region near the bottom of the well, where this Boltzmann factor is very large. In the numerator, we have the v naught, we have the Jacobian, the 4 pi r squared, which comes out of the change to polar coordinates. We have our Boltzmann factor again, e to the minus beta u of r dr, and this delta function now is all that's left of the original delta function, r minus r star. So this integral now is pretty easy to do. Okay, so we have done the numerator. The numerator is a rather easy integral, and the denominator is also going to be pretty easy, but we're going to have to do some tricks first, okay? So the idea is that we look at the bottom, near the bottom of this Morse potential, and we do a Taylor approximation. And we say, well, locally that looks about like a parabola. And so if I were to expand this to second order, I would get the value of the energy at the bottom, plus there's no first order derivative term. There is only a second order derivative term here because we were at a stationary point. And so I've got a reduced mass times some frequency, which I don't actually know, divided by 2, multiplied by the distance from the bottom of the well squared, okay? But we can find out what that effective frequency would be by doing a Taylor expansion of my energy landscape U right here at the bottom, and I of course want to match the second derivative of this potential, evaluated here at R naught, with the second derivative of the one that I have here. Bit of a roundabout way of going about doing things, but very familiar with this form of writing a harmonic oscillator potential and the version of that harmonic oscillator potential in a Morse set of potential energy coordinates and parameters is not something that I know by heart. Okay, so you can interconvert the two. This is your effective recipe for getting this unknown frequency from the known reduced mass and from the known R naught and the known E naught and A. You now have a recipe for what that omega naught is. Okay, so now the take-home message here is that downstairs in this integral, we're going to say that thing looks like a Gaussian, right? So it looks like a Gaussian because we're going to take this quadratic function and put it in the exponent. All right, and now Gaussian integrals are usually rather easy to do. Okay, so now I'm going to trust that you guys can go from here and this recipe for getting the omega naught, plugging it in down here, doing the Gaussian integral, and now we know this Boltzmann factor that lives inside this rate expression, right? So these are the results. We have LR to the minus 1 times EXP minus beta delta F at R star. This is going to be equal to R squared. Okay, so after doing the Gaussian integral, we get this denominator term, and this term actually also came from the denominator. These are all the pieces of my rate expression, right? So I cheated here and did all of that while you guys were not watching. So now where do we go from here? This is a pretty complicated and ugly rate expression. And fortunately, this term, okay, so usually this term down here in the denominator is going to be much, much larger than 1, and that's going to allow us to cross off this term and make some simplifications. Now what we're left with, after making this simplification, crossing off this 1, canceling a bunch of terms, we end up with a ratio of R star over R naught squared. This is an exponential. Okay, so if we put all of these things together, out, Okay, so as I was saying, if we take all of these pieces that we've computed so far and we put them all together, we get this expression, which is the transition state theory rate constant evaluated for a dividing surface located at distance r star, at this point arbitrary, along this RAB axis. Okay, and I want to just focus in on each of these terms here. This is the so-called frequency factor, the thing that gives you the correct units. This is the ratio of, if you want, the area of your dividing surface divided by the area of the minimum. This factor out here inside the exponential is going to be 0 if you happen to choose r star equal to r naught. Of course, we know that would be a terrible choice. But as we choose r star going farther and farther out here, that goes to e to the minus beta e naught, eventually becoming as small as possible out at infinity. Of course, when I choose that gigantic r star, I end up with a rate constant that's very big, because the r star over r naught term becomes large. You know, where is the optimum? Well, that is what VTST tells you that we should pick. So VTST is going to be the minimum over all possible choices of r star of KTST of r star. Okay, and so this is basically the recipe for. Okay, so the convenient thing to do in this case is to define K0 to be the omega naught over 2 pi times the exponential of minus beta E naught. Okay, now the advantage of doing things this way is that I can now write K TST of R star as K naught times R star squared over R naught squared times E to the minus beta U of R. Okay, so now we get all of our R dependents, sorry, this should be at R star. And now I get all of my R star dependents inside this one compact little function. I've lumped everything that doesn't change when we change our dividing surface into this prefactor K naught. And so now what we're going to do is we're going to plot the logarithm of K TST at R star divided by K naught. We're going to plot that versus R star over R naught. So these are the axes. That's going from about 4 to about 3.5, and the R star over R naught is going from about 3 to about 5 or 6. When the beta E naught value, that was a parameter in our original Morse potential, is 20, then the minimum value of the rate constant occurs when I choose my R star to be about 5 times the value of R naught. When beta E naught is about 8, it has shifted to be about 4.5 times the value of R naught. And that I think is surprisingly far, right? So if you think about it, the optimal distance to choose for your dividing surface, approximately 5 times the value of R naught. I always find that kind of surprising that you would think that you just stretch a bond to one multiple of its own length and that it will be completely broken. But the VTST calculation suggests that the optimal place to place that dividing surface is a little bit farther away than you would expect, at least for a Morse potential. Okay, so all of this stuff is specific to a Morse potential. Okay, so hopefully in this example, you got to see how to use the machinery for doing a generalized transition state theory rate calculation. Key things that popped out of this that would not have been in the rate expression if we had used other kinds of theories are factors like this, which automatically account for the entropy of the area of the different shells associated with different dividing surfaces. And of course, you got to see this process in action where you optimize the location of your dividing surface along your trial reaction coordinate, and that gives you this VTST rate estimate.